energy and climate constraints are forcing us to change our energy production model, and for that, different options are on the table. It turns out that renewable energies as they are presented, particularly wind and solar, require a lot of metals. These metals lead us to a new section concerning mining resources. What proportion of resources is extracted from the ground? What does it represent? What is this metabolism, this part of the Earth's metabolism? To begin with, I suggest you consider a figure. Human production is more significant today. It weighs more than the entire biosphere, all the living beings that make up the biosphere. This is a recent article from Ron Milo's laboratory, which was published in Nature. Ron Milo's laboratory had already conducted the study on the distribution of biomass according to different species groups that we had seen previously. Here, there are two figures to remember. The total mass of buildings and infrastructure, everything produced by humans, is more than the total global biomass. Another figure he provides is that the total mass of plastic produced by humanity, 8 gigatons, is greater than the total mass of animals on Earth. Another figure extracted from his paper shows here that this increasing production of goods extracted from the Earth, this anthropogenic mass, is undoubtedly surpassing the biomass. He estimates the pivotal period to be around 6 years, up to 2020, so we are in it. And what is interesting about this curve is that this mass doubles approximately every 20 years. So obviously, if we continue at this current pace, we will have an essentially artificial Earth. And we can also see in the various elements that what represents the largest part of this artificialization, of this anthropogenic mass, of what has been produced by humans, is on one hand cement, and then what he calls aggregates with gravel, etc. That is to say, in fact, all of this is essentially artificial rock, roughly speaking, represented by buildings, roads, etc. Another way to look at it is this. If we consider everything that is extracted from the Earth per year, we arrive at a figure of 90 billion tons per year. And again, you have different parts here. The yellow part, which is called non-metallic, and the blue and gray parts here are parts we have already somewhat covered. The blue part is the metals, which we will discuss in a moment. The gray part is fossil fuels such as coal, gas, and oil, here. And there, the non-metallic part is essentially sand. Green corresponds to biomass, which is essentially wood. Sand is an important mining resource, the most significant in volume. It represents 40 billion tons per year. It is a resource primarily dedicated to construction. We use it to make concrete, which allows us to build cities, etc. And why is this a problem? It is a problem for two reasons. On the one hand, there is currently a shortage of sand in a number of regions around the world, which is causing local environmental problems. And furthermore, where there is scarcity, there is wealth. And where there is wealth, there is trafficking. And we are seeing the emergence of mafia-like practices around sand trafficking, which was unimaginable a few years ago. Now let's move on to critical metals. What are critical metals? I have indeed chosen this figure from Mineral Info by BRGM to illustrate it for you. These are types of materials, in this case metals, that are subject to two major constraints. The first is that they are used in the industry, and we do not know how to replace or substitute them, or very little. And on the other hand, they face supply risks, meaning they are either rare or produced by countries that control access and thus limit the possibility of obtaining them. How do you interpret this diagram? The redder it is, the more critical it is. The greener it is, the less critical it is. And I have highlighted the rare earth elements in purple here, which are not that rare because on the Earth's surface, but they are at high risk of supply disruption because they are primarily controlled by China. So why is this important? This figure is taken from a report by a Dutch think tank on the energy transition and presents the reasons why it is important. So how do we read this figure? First, on the right here, what is needed to produce offshore wind, onshore wind, or photovoltaic energy? On the left, the countries that control or where the production of the elements comes from. And then here, the list of elements. So let me give you an example. To produce wind energy, whether on land or at sea, we need neodymium for the components. This neodymium represents a significant amount, 1630 tons. These 1630 tons come almost exclusively from China and Australia. All right? So we can clearly see the flows here. Therefore, we understand why this material is considered critical, because it is controlled by two countries. If these countries ever stop supplying, we can no longer use neodymium and there will be no wind power production possible outside of China and Australia. Another example, if we take indium used for photovoltaics, we see that indium comes from a number of countries, particularly South Korea, Canada, and China. From the perspective of an energy transition where we would significantly develop renewables, particularly wind and photovoltaic, there is a substantial increase in various metals. Here you have the consumption, or at least the necessary quantity, of praseodymium, dysprosium, terbium, neodymium, and indium of these 5 rare earth elements. For the production in 2020, and as we move forward by a decade each time, you see that, for example, for indium, there is an absolutely considerable increase by a factor of 20 or more compared to the production in 2017. Similarly, for the development of all electric systems and electric mobility, particularly electric cars, today's batteries require lithium and cobalt with current technologies. And this is a projection from the International Energy Agency, which shows that compared to the amount of lithium and cobalt in 2017, it would be necessary to considerably increase the number of tons of these 2 metals within the next 20 years. So this scenario is what we call the sustainable development scenario, meaning the scenario of sustainable development where a very large part of mobility has become electric. There is, of course, an obvious relationship between the number of electric cars and the amount of cobalt and lithium needed for these batteries. So we can clearly see that there is a problem with access to these metals and there is pressure on the resource. And in order to meet the demand, we will need both deeper mines, less energy consuming and more efficient extraction processes, but also, and most importantly, massive recycling. However, recycling today is very limited for these metals. So here, this is the periodic table of Mendeleev with the critical metals represented here in different color codes. The color corresponds to the degree of recycling. What we see is that those which are very rarely recycled, such as rare earth elements, are shown here in red, meaning less than 1% of the quantity of these metals currently in the economy is recycled. The more the color shifts towards blue, the more the material is recycled. It is clear that overall, a number of these materials need new recycling channels and new processes, and that this is not yet in place at all, which increases the pressure on resources, since all the rare earth elements needed by the industry today are extracted from mines. The use of these metals allows me to transition to the topic of pollution, because these metals are used in a vast number of electrical and electronic compounds. The production of electronic waste today is absolutely considerable. I have noted here a figure that to me is significant. The electronic waste worldwide in 2016 corresponds to the weight of 4,500 Eiffel Towers. So 4,500 Eiffel Towers? I find it hard to imagine, but that's what the world produced in 2016 in electronic waste. These wastes consist, among other things, of these well-known rare earth elements or these critical metals that will now need to be recycled. And this recycling rate is very low. Here you have the different proportions of electronic waste recycled by continent. So Europe is the best in the class, but despite that, it remains very limited, 35%. It's 0% in Africa, 6% in Oceania, 17% in North America. There is an absolutely considerable amount of work to be done. So we have just seen a number of pressures exerted on non-living resources, mineral resources, and energy. And now we will move on to pollution, that is the way waste accumulates in the atmosphere, hydrosphere, and lithosphere. If we refer to Rockström's limits model, we will essentially cover 2 subjects that are very important, and among the most concerning ones. The first is the accumulation of phosphorus and nitrogen. It is the disruption of the phosphorus and nitrogen cycle that is considered a priority, the second priority after biodiversity erosion. And then we will address global warming, which mainly results from the accumulation of greenhouse gases. Eutrophication is the process where the accumulation of nitrogen and phosphorus in aquatic ecosystems, whether freshwater or marine, causes a disruption of the entire ecosystem, with consequences, as we will see, that are quite catastrophic. Nitrogen and phosphorus primarily come from fertilizers used in agriculture. They accumulate along rivers, either in lakes or in seas. This indeed causes the appearance of what are called algal blooms, which are significant proliferations of algae that come to the surface and produce an enormous amount of matter. Matter is then degraded and dies, and the bacteria that degrade it proliferate in turn and consume a lot of oxygen. This causes what are called oxygen holes, if you will, entire areas where there is no oxygen, and what are called dead zones. Here are some images to give you a visual idea of what we're talking about. Here we have Chinese children swimming in algae-filled pools. So they are in the sea, but there is an absolutely remarkable bed of algae. The fisherman next door laments because he no longer has any fish. Why? Because in fact the fish died of asphyxiation. There is no longer enough oxygen in the water, and it kills absolutely all the local biomass. And then the one at the bottom is a representation. It's a satellite view of a coastal area where you can see an algal bloom, giving an idea of the scale of these processes. On the next slide, it is indeed a clear representation of the areas affected by this eutrophication, the marine zones, on a global scale. We see in red the small red dots. These are areas where locally the dead zones have been identified, and the blue areas are the areas where not only are there problems at the coastal level, but this problem, this dead zone, extends over much larger areas. And we see that, in fact, the accumulation of nitrogen and phosphorus and their entry into aquatic ecosystems cause a decrease in the capacity of these ecosystems, even leading to the death of ecosystems on very, very large scales. In this section, we will address climate change, the climate crisis, which essentially stems from atmospheric pollution. The pollution of the atmosphere by gases, known as greenhouse gases, GHGs, with the most well-known being CO2, is presented here in black and red carbon dioxide. There are others, methane, nitrous oxide, and then fluorinated compounds, which have an extremely high warming potential. So these molecules accumulate in the atmosphere, and very quickly they trap infrared radiation, which will locally increase the temperature. When we have an accumulation of these gases over decades and decades, we end up with a change of a few degrees across the entire planet. Specifically, since the beginning of the industrial period, we have seen an increase of about 1 degree. It is visualized here. There you have the representation of the world. Each small circle is a small map of the world. In red, these are temperature points that are warmer than average. In blue, these are moments that are cooler than average. And in gray, these are places where we don't have the data. And if we look from 1850 to 2016, we can see at a glance that the climate across the entire planet tends to warm, especially over the last 30 years, where we see that the red part is really very significant. So why exactly is this global warming really troublesome? And what are the serious risks involved? I took this figure, which attempts to summarize all the problems it poses in a comprehensive manner. Climate change, the climate crisis, is leading to a profound transformation of all systems. The physical system, the biological system, and of course the human system. So the physical system includes, for example, the melting of glaciers, the melting of snow, and the possible thawing of permafrost. Here in blue we can see the various different places where ice has started to melt, particularly in the Arctic and Antarctic. And to measure the risk or the problems posed, there is also this small scale here. A single bar, the confidence level is low, so we don't know if the effect is significant or confirmed. Now, the more bars you have, the more important it is. And you can still see that on a global level, across all systems, we have a lot of established facts and problems whose degree is significant. On the one hand, to return to the physical system, the melting of glaciers, floods, droughts that disrupt the functioning of the hydrosphere, coastal erosion, or the rise in sea levels will pose problems for biological and human systems. These physical systems impose problems on biological systems, primarily agricultural systems and wild ecosystems. We have the occurrence of wildfires. Indeed, we could add more here, since last year in Australia was particularly marked by very intense wildfires that are not even shown on this map. We have forest fires, we have a degradation of the functioning of marine ecosystems, etc. For human systems, it is essential to recognize the significant pressure placed on agricultural systems and livelihoods, health, and the economy. To summarize, in a perhaps more readable system, we have represented here the most important problems that this will pose in the coming years for our civilizations, namely the degradation of water resources, a shortage of water due to drought, and thus agricultural production problems, with a number of agricultural ecosystems likely to suffer from climate change. the increase in cyclones and floods causing sometimes enormous damage, and finally, significant human migrations on the order of tens of millions, or even hundreds of millions or more, depending on the degree of change that will occur and the impacts it will have on different parts of the world. This graph, published in Nature in 2019, synthesizes the major types of risks posed by climate change and the number of inhabitants who would be affected by this type of risk. Each point represents 10 million people, and there are 3 blocks. If the climate increases by 1.5 degrees, if the climate warms by 2 degrees, if the climate warms by 3 degrees, to give an example, for instance, if the climate warms by 1.5 degrees, there is minimal impact on the agricultural system because only 40 million people will be affected. On the other hand, if we reach 2 degrees, 360 million people are affected, and if we reach 3 degrees, 1.8 billion people are affected, and we can take each category like that. Water stress, which is already significant with a warming of just 1.5 degrees, affects 3.3 billion people. It can rise up to 4 billion. Exposure to heat waves, once again, is expected to affect around 4 billion people, and it could rise to approximately 8 billion, which is nearly the entire human population by 2050. So now we are going to look a little more closely at these different greenhouse gases to better understand where they come from and how they are emitted. In this diagram, we have represented all greenhouse gases in gray, which come from different sectors of activity. In fact, practically all sectors of human activity: energy production, industry, transportation, agriculture, deforestation, buildings, water, and waste. All of these greenhouse gases, about 50 gigatons, now a bit more because this slide is from 10 years ago, we are closer to 60 today, is actually the sum of different effects caused by different molecules. The first one, which is often talked about, is CO2, which represents roughly 75% of the total production of warming power. Next, we have methane, which accounts for around 20% of the warming potential, depending on how it is measured. And then there is N2O, nitrous oxide, which mainly comes from agriculture and accounts for around 6%. And finally, the molecules, the sulfur compounds, that are extremely warming, which have an extremely strong warming power, but are produced in very small quantities and still contribute about 2% to global warming. This slide essentially presents the same type of information as the previous slide in more detail and in a different form. We see that carbon, CO2, shown here in blue, which comes from energy, represents the largest portion of greenhouse gases that cause warming. There are other significant sources of CO2, notably transportation and international transport. Methane, shown here in green, also represents a significant portion. It is notably produced by energy production, the agricultural sector, and the waste sector. Nitrous oxide in purple also represents a small fraction, which is mainly seen in agriculture and industrial processes. And then the gray part here corresponds to the greenhouse gases that come from deforestation. It is the combination of all these factors that results in the production of greenhouse gases over about 5 years, around approximately 55 gigatons of CO2 equivalent. In summary, it is the combination of these factors, these gases and sectors, that contribute to producing the equivalent of 60 gigatons of CO2 equivalent. These are the greenhouse gases that need to be either reduced or offset to achieve a neutral system that no longer emits greenhouse gases into the atmosphere, allowing climate stabilization. A complementary diagram shows the distribution of greenhouse gases by country or geographical area, along with a timeline. And so this curve is the mirror curve, if you will, of the amount of fossil fuel that has been consumed by humanity, as we saw earlier. We see a slow increase followed by an extremely rapid acceleration starting from 1950. All countries, all regions are affected, and we have a greenhouse gas production, a greenhouse gas emission that has been fundamentally exponential until very recently. So what are the scenarios based on these curves and these considerable productions? Today we are in the range of 50 to 60 gigatons of CO2 equivalents in 2020. The IPCC proposes different types of scenarios. If there is no effect at all, if there is no modification of our energy system, we will continue to emit greenhouse gases at a rate based on previous curves that will lead the climate into an extremely uncertain and unstable trajectory with a warming between 4 and 5 degrees. This is what is called the scenario, without any particular climate policy. With current climate policies, that is, with the commitments made by a number of countries, we can imagine a climate stabilization around 3 degrees between 2.8 and 3.2, which means an increase that corresponds, if you remember what we saw earlier, to drastic effects on most of the inhabitants of the Earth. Now, we see that with all the commitments made, particularly during the Paris Agreement in 2015, much more will need to be done than what has been proposed to stabilize the climate with an increase of 2 degrees and even more so at 1.5 degrees. Here is the curve showing what's in the pipeline, and there is the curve we need to achieve. Another way to grasp the magnitude of the challenge ahead of us is to look at the year 2020, which was an exceptional year as the global economy came to a halt, or nearly so, for several months, with countries around the world being in lockdown. And yet, despite everything, with this extraordinary effect, the reduction in CO2 emissions is ultimately quite limited. We don't have the final figures yet, but it's approximately between 7 and 10% of the overall emissions of a normal year overall. So that's why what Carbon Brief says, in my opinion, gives the scope, gives the measure of what needs to be done to stay below the 1.5 degree threshold. The largest drop in CO2 emissions ever recorded, which occurred in 2020, must be maintained every year. This means that from now on, every year, we must achieve the same reduction as this year. Moreover, it's not about going back into lockdown in 2021. We would just achieve the same level. It's about doing this plus that, etc. until 2050. Another way to represent the problem is to visualize here the curve of CO2 emissions and then the target to be achieved by 2050. In fact, this target is not just a time frame, it's also what we call a carbon budget, which is the amount of CO2 or greenhouse gases that we can release into the atmosphere while staying under the 1.5 degree limit or even the 2 degree limit. These budgets represent the amount of greenhouse gases we can emit. Inevitably, the longer we wait to implement policies to bend the curve, the more the budget shrinks and the steeper the slope becomes. This script may be too long for the scene. For optimal results, consider shortening it. The production of waste from human metabolism is not limited to nitrogen, phosphorus, and carbon. There are many other types of pollution. I won't address all of them here. Just one figure, the quantity of molecules created by humans is very significant. According to sources, there are around 100,000 new compounds, meaning their toxicity has not yet been estimated, so we can see that these numbers are very significant. And for the well-documented phenomena that pose problems, I have identified 3. The first is air pollution, whether it is indoors or outdoors, such as in homes or offices, for example. If combined, it is now indeed actually the 4th leading cause of death globally on Earth. First, we have approximately 10 million deaths related to hypertension each year. The second is tobacco, 7 million people. The third is diabetes, 6.5 million. And the fourth, with 4.9 million deaths per year, is air pollution. Here, a visual representation of the state of aquatic systems, in red, an overall water quality that is poor to very poor. In blue, an overall good quality of water. I think we don't need to go into detail. There is a lot of work to be done. Finally, a few slides on plastic, because it is indeed very often mentioned and represented in the media. This is a very significant production. This slide dates back to around 300 million tons per year. On top of that, a large portion of these plastics are recycled, incinerated, or landfilled. However, a significant fraction continues to enter the water, accumulating in the oceans. So where exactly and by what mechanism or process? 2 slides to address this. The first is the significant amount of plastic waste that is not properly treated. The darker the country, the less this is the case. So we see that, roughly speaking, OECD countries, even though there is still a lot of effort to be made, manage plastic resources quite well. We are talking about a few % that are not properly treated. In contrast, in developing countries, particularly in Africa and Asia, almost all plastics are not properly treated. And so we come to this important slide, which is from a work published in 2017, which shows that, in fact, if we look at all the plastics that are in the oceans today, the largest fraction comes from a few rivers, particularly in Asia, which produce the majority of the waste that accumulates in the oceans. It is both bad news because the volumes are enormous, but also good news because it allows us to imagine more concentrated modes of action, since the basins where these plastics are produced are ultimately quite limited.